In this video, we're going to talk about sampling, specifically Nyquist sampling theorem. This cosine wave represents a signal which has a frequency of 1 hertz. We see that because every repetition of the wave repeats every second. So there are 1 cycles per second. So this wave has a frequency of 1 hertz because hertz equals cycles per second. Nyquist sampling theorem says that the frequency of the sample must be greater than or equal to 2 times the maximum frequency of the signal. So for the signal we just looked at, the frequency of the signal was 1 hertz. That means the frequency of the sample must be greater than or equal to 2 times 1 hertz. Or the frequency of the sample must be greater than or equal to 2 hertz. This gives us the frequency that we should sample the signal at if we want an accurate representation. That's why we use Nyquist sampling theorem, because we want an accurate representation of the signal. Now, the sampling theorem matters when we want to take an analog signal from the real world, something like light intensity, sound, voltage, current, even resistance. We want to convert that to be able to store it in a computer, which stores digital information. So in this case, we're going to sample this frequency that we're looking at a specific rate. And we have determined that rate to be at least 2 hertz because the frequency of our sample is 1 hertz and we want to sample it at least 2 hertz. So I'm going to draw a blue dot at every point we're going to sample. So we take our first sample. 2 hertz means 2 times per second. So evenly 2 times per second, we will take a sample. So we'll say that we've stored this information in the computer. When we reproduce this signal, it will look like this. Basically, the computer connects the dots. So I'll connect all of the blue dots to give us the representation that we recorded when we used Nyquist sampling theorem to record the signal. And we can see it's pretty close to the sine wave. Now we'll go back and say we sampled this signal at 1 hertz instead. Say we aren't using Nyquist sampling theorem and we actually sample this signal at the same frequency that it occurs. So that means 1 time per second. So I'm going to draw a circle at 1 time every second. Now I'm going to connect the dots. Does that waveform represent the signal? Obviously not. So if we were to sample this signal 1 time per second, not following Nyquist sampling theorem, and we recreate the signal that was stored in the computer, it doesn't look anything like the signal that we actually want to capture. This is why Nyquist sampling theorem is important. What we've done here, this is called aliasing. This is when we capture the signal at an incorrect frequency, and when we go to recreate the signal that was captured, it is completely wrong. It is not representative of the signal. That's what aliasing means. So when we actually measure a signal from the real world into a computer, we use Nyquist sampling theorem to determine the rate at which we're going to measure the samples. So in the previous example, I drew a circle for every time that I measured the signal. It looked something like this. Now what that means is that I am taking a measurement at every point in time where there is a sample. So I'm taking a measurement of this amplitude. Let's look at the axes. So the y-axis is representing the amplitude of the signal. X-axis is representing time. In this case, it's in seconds. So every time that I draw a circle, my computer is recording the amplitude of the signal at that very time. So when I take a measurement, it will record two things: the time from the x-axis, so we'll say 0 seconds, and it will also measure the amplitude. In this case, so we have 1, 2, 3, 4.5. So this would be 4.5 volts. Here we have 1, 2.5, negative 2.5 volts. So the amplitude at the very first measurement was 4.5 volts. This is our very first measurement. Our second sample, time equals 0.5 seconds. Amplitude, measured in volts, is negative 2.5 volts. At time 1 second, the amplitude is 4.5 volts again. And so it repeats. So this is the data we are actually recording when we are converting an analog signal to a digital signal. Then when we go to recreate the signal, we can do so because at 0 seconds we were at 4.5 volts. At 0.5 seconds we were at 2.5. At 1 second 4.5, and so on. And then we recreate the signal from the data that we gathered. This is basically how analog to digital conversion happens.